Okay, so let's forge ahead into some more interesting and fun one-dimensional kinematics problems and wrap this chapter up. Again, refreshing our memories to where we were last time, we were talking about these kinematic equations, and I spent some time suggesting that you try to memorize or become very familiar with at least these first three equations because they come up so often and they're so powerful in terms of solving one-dimensional kinematics problems. Again, the variables and what they stand for are listed here. One more time, I'll just mention that a lot of times I'll put a little F on my V final and X final, so it helps remind me that it's the final quantities. However, that's obviously optional. Now, before we continue and start to look at solving one-dimensional kinematics problems, I found through the years, the many years I've been teaching physics, that oftentimes students make mistakes in problems, and they're usually very small mistakes dealing with things like units, or many times it's just a sign error. So many times it's not the math or the physics idea that's the problem, but it's an incorrect sign. They call something positive when it should have been negative, or negative when it should have been positive, and that sort of thing. And if you make one sign error in a physics problem, unfortunately, that's it. You're going to get wrong answers. And so what I found through the years is that this activity, this little exercise page, is a good way to nip any issues with signs in the bud before we get into the problem-solving process. And the way this works is there's three different problems here. They're each along a column in this activity page. So there's basically three problems, right? One along each column there. I'm going to go through the one on the left with you to help you understand how this works, and then I'll let you do columns 2 and 3 on your own. And so what we have here is what we call motion diagrams. Okay, a motion diagram is a diagram that you want to think of as just being following an object, but taking, if you could imagine the object having a velocity vector sticking out of it as it moves, you would look at a series of snapshots of the velocity vector. And so, for example, over here on the column on the left, we see V0, which means the object is starting at this position right here, right? And it's moving to the left. We see an arrow pointing to the left, and it's got a length of, whatever you want to call that on your screen there. And so we have an object that's initially moving to the left. A little while later, we look for our next arrow, and we find out there's an arrow to the left here, but it's not quite as long. Okay, remember the length of the velocity arrow is proportional to how fast the object's moving. So in this case, the object's still moving to the left, okay, but it's slowing down. It isn't moving quite as fast as it was originally. And then over here we see V, which is, our final velocity in the series of arrows. And here we see that the velocity is again to the left, right? But the object's moving even slower than it was previously. So what we really have here is a series of three snapshots, 1, 2, 3, showing the progression of the object. And so what the motion diagram is telling us is that this object starts here, okay, and it moves to the left, and it's moving quickly at first, and then eventually it slows down and is moving much slower by the time it gets to this position. Okay, so that's kind of the picture of it. Now, what they want you to do in this activity is indicate whether we're at the open dot here. One of the motion diagram arrows will have an open dot shown. You also see that labeled on the axis, the 0 will be labeled very clearly. It actually has the word 0 written underneath it. So this is my 0 on my x-axis, which makes this the positive x-axis, and of course this direction over here would be the negative x-axis. So as I consider that, and it wants me to indicate whether the position, where the open circle is here, is the object when it's at that position, is it at a positive position, a negative position, or is it at position 0? Well, obviously it's to the right of 0, and so I would indicate that this is a positive position. Right? When the object is right at this location where the open dot is, it would be at a positive position on my x-axis. Okay? The velocity where the open arrow is, when the object is at this position where the open dot is, it's moving to the left, and so I know that the velocity is going to point in the leftward direction, or it would be a negative velocity at that point. Now, to answer the acceleration, again, we've learned that acceleration and velocity are two different things, as our little Albert Einstein cartoon guy here says. And so we have to think about the motion. Okay, the motion is that an object's moving to the left, and as it goes, it's slowing down, right? It's going slower and slower as it goes to the left. And therefore, if it's slowing down, that means the signs of the velocity and the acceleration must be opposite. So if the object has a velocity to the left in the negative direction, the acceleration here must be positive. Another way to get the direction of the acceleration is to look in your motion diagram. It generally points from where the arrows are shorter to where the arrows are longer. And so the acceleration here points from left to right, indicating that the object, if it's moving to the left and is accelerating to the right, with the opposite signs here, the object should be slowing down. And that's what our motion diagram says. Now, looking at our situation in the middle column and the column over here at the right, I just want to clarify that there's actually two different points in each of these problems that they want you to consider. Point number 2 is labeled there, and point number 6 is labeled there. And in this particular motion diagram, obviously the object's starting here, where V0 is, and it's ending up over here. This motion is along an axis. In both the second column and the third column problems, the motion is along an axis. It's one-dimensional motion. It's just that the object's moving initially to the right, and then it stops right here, and then it comes back to the left. And if we drew all those arrows on top of one another on the axis, it would be cluttered, and we would have difficulty seeing what's really happening. So anyway, in the second column here, for example, when they say position 6, they want you to indicate whether when the object's here at position 6, is it at a position that's positive, negative, or 0. Okay, velocity 2, if they want you to rate the velocity 2, you look at the velocity at position 2. In this case, the velocity is to the right, and they want to know, is that a positive velocity, a negative velocity, or a 0 velocity. And same thing over here in the third column. The motion is up along the axis and then down along the axis. We just separate the arrows off to the side of the axis a little bit for the upward and downward paths so that you can distinguish between them. So go ahead now and complete, do the best you can to answer the signs, to try to answer correctly whether the sign of the positions, velocities, and accelerations at these points are positive, 0, or negative in each of these two problems here. And we'll see how you do. Okay, so how did you do? Here are the answers. Again, we see our answers that we had worked together on column 1. And in columns 2 and 3, if you check over your work, first thing I want to say is that it's very unusual for students to get these all right, okay, the first go around. So if you missed some of these in columns 2 or 3, do not panic. That's pretty normal. If you got them all right, if you did get them all right in columns 2 and 3, the signs here, you're in good shape. That means that you have, hopefully your understanding of signs here is going to be good, and it will cause you hopefully less problems than some other students. But most students miss at least a few of these, sometimes many, and it's important to go back and just go through and make sure these make sense. So ones that usually give students, well, let me just go to column 2 here. Here's the 0. So on this particular axis, anything over in here, any positions over in here would be negative. So both positions 2 and 6, if you notice, are to the left of the 0, and therefore they're at negative positions. So that takes care of these two answers, right? The velocity, keep in mind that the velocity sign is related to the direction that the velocity arrow is pointing. At position 2, it's pointing to the right. That's the positive direction. At position 6, the velocity arrow is pointing to the left. That's the negative direction. So we get the direction of the velocity, the sign of the velocity, simply from what direction the object's moving. Again, to get the accelerations, this is where we have to consider the motion and relate it back to the velocity. In this particular problem here, the object was moving to the right and slowing down. If it's slowing down, the signs at this point of the velocity and the acceleration should be opposite. So at position 2, we saw that we had a positive velocity, which means we have to have a negative acceleration at position 2, okay, because it was slowing down. Signs have to be opposite for velocity and acceleration if it's slowing down. However, after it stops at this point here, and then it comes back to the left, it's actually speeding up as we read through the progression of the arrows, right? Position 1, 2, 3, 4, 5, 6, or I'm sorry, I missed that one. Position 1, 2, 3, 4, 5, 6, 7. So we've got 7 positions listed there in our motion diagram. And as it comes back after position 4, as it gets to position 5, 6, and 7, we see that it's moving to the left and speeding up. So if the object's speeding up, that means that the velocity and the acceleration in this part of the trip have to be the same sign. At position 6, we see the velocity was negative. It points to the left, which means if the object's speeding up, we have to have a negative acceleration as well. And so similar sorts of reasoning leads to the answers here in the third column. The one point that generally causes students a lot of problems is this one right up here at the top, point 4. Most students will say, well, at position 4, that's its turnaround point, so I understand that its velocity here, its velocity at position 4 is 0. That makes sense. It's up at its very highest point. It's in motion, has just a blink of an eye, or just an infinitesimal moment there where it stops up at the top of its trajectory, right? If we throw a ball up in the air, we know it goes up. At some point, it's going to just stop for an instant, and then it's going to come back down. So most students get that the velocity up at the top is 0. What they don't get is that the acceleration at position 4 is negative. How can it actually have an acceleration when it has no velocity? Well, look at it this way. Acceleration is describing how the velocity is changing. So if you agree that the velocity is 0 here at position 4, and if the velocity doesn't change, then that means that the object would just stay there forever. If it has no velocity and has no acceleration, then obviously the object is sitting at rest and will remain there forever. And obviously when we throw something up, we know that it doesn't stay there, it comes back down. So the velocity is clearly still changing at the top. Therefore, it has to have some acceleration. In what direction is the acceleration? Well, let's think about what's happening right before the object's at the top. Right before the object's at the top, it's going upward very slowly, and right after it's at the top, just an infinitesimal fraction of a second after it's at the top, it's heading downward. Is the velocity changing? Yes, it is. It's still changing. Even though the velocity is small, right before, just a blink of an eye before it was at the top, it was going up, and just a blink of an eye after it was at the top, it was going down. Therefore, the velocity, even at point 4, while it's not moving, is in the process of changing, flipping from positive to negative, and therefore the acceleration is in the negative direction. On the way up, it's slowing down, which means if the velocity is positive, the acceleration has to be negative. On the way down, it's speeding up. The object's going and falling faster and faster. If it's speeding up and the velocity is negative, the acceleration has to be negative as well. In fact, we find that the entire time the object is in the air, tossing it up and back down, the acceleration is downward in the negative direction. Okay, so think about this. This is a difficult point there for many students, and is one of the top 3 misconceptions that introductory physics students have. So it may take you a little while to get over that, but just keep in mind, even if the velocity is just changing direction, it's still changing and still has an acceleration. So again, if you think about that, just for the instant it's at rest, but right before and right after it's moving. It was going up, then right after it was at the top, it's going down. Therefore, the velocity is still changing. Again, it cannot have a 0 acceleration here because that would mean that the velocity would maintain whatever value it had here. And if it wasn't moving, it would not begin to move. And of course, we know that's not correct. Objects, when we toss them up into the air, do not hang up at their highest place. They actually eventually come back down. So continue to think about this, and hopefully as you study and work on problems some more, this will make more sense as we go. Okay then, so that takes us to our first one-dimensional kinematics problem that's a little more interesting. I should say our first interesting problem, and we actually have a fairly realistic problem here. It says, suppose you're driving down the highway at 56 miles per hour, and of course in the international system of units we don't use miles per hour, that's an English unit. It's very familiar to us that drive in the United States because our speed limit signs on our highways are still in miles per hour. But in the international system, the standard unit is meters per second. And so it's important, I think, as an American student or students who are studying in America to try to relate the highway speed, which is about 56 miles per hour, to the speed in meters per second. And if you remember that 56 miles per hour is 25 meters per second, okay, so about highway speed is 25 meters per second, that allows you to get a sense as to how fast this really is. If I'd have said 25 meters per second, said the car was moving at 25 meters per second, you would probably not have much idea what that meant. But now that you know this, if I say 25 meters per second, now you're going to say, oh, that's about highway speed. Okay? So anyway, let's read this problem again. It says, suppose you're driving down the highway at 56 miles per hour, which is 25 meters per second, when a deer jumps out onto the road about 63 meters down the road from you. You cannot steer around the deer, and your car can decelerate at only 5 meters per second squared. If the deer stands still and you react instantly, will you hit the deer? Okay, so this is a realistic problem, right? I mean, we can imagine this happening. We're driving down the road, a deer jumps out on the road, it's frightened, it just kind of freezes and it stares at us in the middle of the road. We cannot, steer around it. We might go over the edge of the embankment or on oncoming traffic. And so we have to just hit our brakes and slow down, and hopefully we stop in time and keep from hitting the deer. So step number one in solving these one-dimensional kinematics problems, and usually with almost every physics problem, this will be step one, and that is to draw a sketch. Okay, it's really important to visualize and understand what the problem is saying. Many times you have to read it several times, and you have to start to draw a picture and a diagram of what it's saying. Now, it didn't tell us whether the car was going to the left or the right, but most of the time, we typically, I guess because we read from left to right, and the right is towards the right is the positive direction. In this case, I decided to make my car moving to the right. And so what I did was, of course, I use clip art here, but it doesn't have to be fancy drawings. I mean, you could just draw a car like this, something like that, just a box with a couple wheels, and you could draw a deer with a head and a body and some legs and some antlers or something like that. So it does not have to be fancy, but you do need to have a sketch, okay? And so again, I use clip art. So here I see a picture of the car, and it's moving to the right. I chose to have it moving to the right at 25 meters per second because that's what 56 miles per hour is. We want to use standard units here, right? And I decided to start the car at position 0. Why? Well, it didn't tell me what position the car started at on the coordinate system, which means I get to choose that. And so usually we select our object starting at position 0. It kind of simplifies the problem most of the time. We don't have to do that, but oftentimes starting the object at position 0 is a good idea. And so we see our car at position 0 moving to the right at 25 meters per second. We have the deer down here, down the road, 63 meters down the road from us, 63 meters in the positive direction, down the road from us. So I put the deer at position 63, and they're basically standing there at rest. And then we're told that the car can decelerate, or in other words, slow down, at 5 meters per second squared. So if the velocity of my car is to the right and it's going to be slowing down, that means my acceleration has to be to the left or in the negative direction. You need to have opposite signs if the car is slowing down. So again, this does not say that the acceleration is negative. Why? Because the problem doesn't know. When the person wrote this problem, they don't know which direction we're going to assume the car is going. Sometimes they set that up for you with a diagram or explain it in detail. But here they didn't. And so if we're going to call our initial velocity positive, then our initial acceleration here, or our acceleration in the problem, has to be negative. So that's a really important part that came out of drawing our sketch. We visualize and we get our dimensions set up and we get our signs correctly understood. At this point, then what we do is we start listing what we know. What we know is that the car starts at position 0, so x0 is 0. The original velocity of the car is 25 meters per second in the positive direction. The acceleration is minus 5 meters per second squared when we put our brakes on. And the problem reduces down to, really, I mean, it's asking, are we going to hit the deer? Well, if the car ends up stopping here, we don't hit the deer. But if the car is going to not stop until here, then we hit the deer. So really the question comes down to is, where is the final position of the car? Where is the car going to end up when the final velocity is 0? In other words, if we stop the car, is it going to end up here or here? So what we're really trying to solve out for here, what we're really going to end up looking for is our x final, and our final speed of the car, final velocity of the car, would be 0. So again, they didn't tell us what to solve for. We have to reason through this and realize, okay, well, I'm interested in where the car ends up stopping. And, that's the position I'm interested in. So I'm going to set the final velocity equal to 0. And our unknown that we're going to solve for here is x final. If x final ends up being less than 63, we miss the deer. If x final is greater than 63, then we hit the deer. It's about that simple. Okay, and this is, again, is a fairly realistic question, which makes this a little more fun as you're practicing solving these problems. So here we have everything set up. Now what do we do? Well, what we do now is we have to look for a relevant equation. Okay, and if you remember our equations, I'm going to go ahead and just jot them off to the left here very quickly. We have v final equals v original plus acceleration times time. We have v final squared equals v original squared plus 2 times the acceleration times x final minus x original. And we have x final equals x original plus v0t plus 1/2 at squared. Those are our big three equations that I mentioned to you about memorizing, okay? If we take a look at those, and again, we want to solve for what? We want to solve for x final. That's what we want. So as I look at the first equation does not have any x final in it. So right off the bat, I'm going to say, well, that's probably not where I want to start anyway. As I look at the other two equations, I have an x final here, and I have an x final here. So when I look at those two equations, I say, well, I've got an x final in both equations. That would be helpful in terms of solving this out. However, this one also has a t in it. And I don't know anything about the time here. And so if I tried to use this equation to start with, I'd have two unknowns. And of course, if you have two unknowns in one equation, you're not going to be able to solve that out. So I'm going to, by default, take a look and focus in a little more on this equation and see what I know in there. Well, do I know v final? Yep, I know the car is going to stop at the end. Do I know v original? Yep, they told me how fast it was originally going. Do I know the acceleration? Yep, it's -5. Do I know x original? Yep, I chose the car starting at x original equal to 0. And x final is what I'm looking for. So it turns out that equation 2 here, this second equation I listed on the page, is going to be the one we want to use. So we pull that one out, we write it down and say, here's our equation. This is our guiding equation for solving the problem the rest of the way. Once we have the equation selected like that through logic and reasoning, and at that point we put in our unknowns, or put in our knowns and solve for any unknowns. So we knew that v final, again, is going to be 0. V original is 25 positive. Acceleration was -5. X original is 0. And that leaves us the x final as the unknown. And of course, if you have difficulty solving the problem from this line down to here to get the answer, what you're struggling with is your math. Okay, I didn't show all the details in the math here, solving that algebraic equation out. But obviously, if you struggle from this step down to here, that is the math. You're not really struggling with the physics, you're struggling with the math. If you had trouble getting to this point, that's kind of the physics, the process of sorting out the details in the problem and selecting the equation. That is really the physics part of the problem. Once we get the equation selected and we get our knowns and our known quantities substituted in, now it becomes a math problem. And so again, this process is just the math, and if we solve it carefully, hopefully you agree with me, we get an answer of x final equals 62.5 meters, and phew, that is just short. If you remember, the deer was standing at position 63 meters, and so we come up just short of hitting the deer, and so that's a good thing in this case. Okay, that was a close one. All right. Now, as we continue along, not every problem we have, of course, will go in an x direction or horizontal direction. Sometimes we have objects that go up and down. And so we're going to talk now about a special type of motion. It's called free fall. And free fall is a state of fall free from air resistance and other forces except the force of gravity. So if you drop something like a rock close to planet Earth's surface, we know that it will fall. Gravity will pull it down, and the object will accelerate towards the ground and hit the ground. If the air resistance is ignored, okay, if the air resistance and other forms of frictional forces holding back the rock are ignored, it's only the force of gravity making the object fall. And so in this particular case, we refer to this as free fall. It's a falling motion free from any other sources of influence other than gravity. Okay, near the Earth's surface, all objects accelerate towards the center of the Earth at 9.8 meters per second squared when they're in free fall. So if we have air resistance is basically neglected, we have no air resistance on the object, every object, no matter how heavy or how light or how big or how small, all objects will accelerate towards the Earth's surface, towards the center of the Earth, really, at 9.8 meters per second squared. And that's when we consider ourselves near the Earth's surface. Now, what do I mean by near the Earth's surface? Well, usually anywhere you've been in your lifetime is near the Earth's surface, even if you've flown on a jet airplane. So we'll say near the Earth's surface, that's within maybe about 10 kilometers of the Earth's surface. So even if you've flown in a jet airplane at 30,000 feet elevation or altitude, you're still near the Earth's surface at that case. And you probably realize that if you've flown in the airplane, it doesn't really feel any different than being on the Earth. You might have even gotten up and moved around on the airplane and used the restroom, or the stewardess came along, or the steward might have come along and gave you a drink and things like that. So even up at the height of an airplane, the acceleration of gravity or the force of gravity feels about the same. And so that's what we mean by near the Earth's surface. Now, it's important to recognize this 9.8 meters per second squared is the magnitude or the size, the magnitude of the acceleration. Obviously, things will accelerate downward towards the Earth. And so our acceleration here is in the downward direction. Now, g, the acceleration of gravity magnitude, is a positive number, 9.8 meters per second squared. Unfortunately, many high school physics teachers and even some college physics teachers probably incorrectly get you confused by referring to g as a negative value. The g value here is a constant. It is a constant of nature. Small g is the acceleration of gravity, the magnitude of the acceleration of gravity, and it's a positive 9.8 meters per second squared. So really what we would say here is the acceleration in this case is minus g. The acceleration is 9.8 meters per second squared, and it's in the downward direction, which is in the negative y direction. So if we're using a standard y-axis where up is positive and down is negative, then the acceleration of things falling, they fall towards the Earth, they accelerate and speed up towards the Earth's surface or towards the center of the Earth, and so the acceleration of freely falling objects is minus g. But g itself is a positive number. Now, many times in problem solving, especially in difficult problems, we may take the 9.8 meters per second squared and we may rough it out as 10, because 9.8 is pretty close to 10, and 10 is a lot easier to do math with. So sometimes for methods of where we're getting a quick and simpler answer, we use g as 10. Today with calculators, most of the time I just recommend you use g as 9.8. Although you'll see that in some problems I will use g as 10 just to demonstrate how that can be done. Okay? On this slide we see a series of photographs. This was a photograph with a strobe light flashing where the shutter was held open, and every time the strobe light flashed it showed the position of an apple and a feather. The apple and the feather were dropped at the same time, and this was done in a vacuum. And so as you can see, the position of the feather and the apple pretty much maintain their position with respect to each other. They fall together downward. In other words, they're both accelerating. The apple's accelerating downward at 9.8, so is the feather, if we have no atmosphere, if we have no air resistance. Okay, obviously if we did this with air, the feather of course would have significant air resistance compared with the apple, and it would affect the motion of the feather. Okay, it would have a greater effect. The air resistance would have a greater effect on the motion of the feather than it would on the apple. The apple smaller and denser. The air resistance acting on the apple might actually be larger in size, but it would have less effect, and the apple of course would fall faster than the feather. Okay, but in the absence of air resistance, if we pump the air out of a vacuum chamber like they did in this experiment, we find out that the apple and the feather, even though they're different in mass, different in shape, and so forth, without air resistance, they fall and accelerate, speed up at 9.8 meters per second per second. That means every second the apple falls, it's moving at 9.8 meters per second faster than it was a second before, and that's going to be true for the feather as well. Okay, every second that it's falling, it's moving at 9.8 meters per second faster than it was the second before, and that's what we call acceleration. Okay, where the object is speeding up towards the Earth's surface. Now, interestingly enough, we can take these kinematic equations that we've been using for the x-axis problems, and again, the big three are right there. We can take those equations and we can doctor these up to work for free fall problems. Okay, if we're in free fall, okay, and ignoring air resistance, then everything that's falling under just the influence of gravity will have an acceleration of minus 9.8 meters per second squared, or in other words, all the objects will have an acceleration of minus g. Okay, so the acceleration in free fall is going to be minus g. So all the a's can get replaced with a letter minus g. Remember, g is a positive number, and so we will take care of the minus sign in our equations to indicate the direction of the acceleration, and we'll put make our a's minus g. Likewise, instead of using x, we typically would use a y. So all of our x's are going to go to y. Okay, so our a's are going to go to minus g to represent the acceleration of free fall. X's are going to go to y, and t, of course, is going to stay the same. Okay, and just to indicate, we're talking about the y direction, we could even put little subscript y's after our v zeros, for example, and v finals. We could put a little y like that to indicate the final y or the original y velocity, and maybe vfy to indicate the final y velocity. That sort of thing. We could do that if we wanted to. But anyway, doctoring up these equations, making these changes, what we find is that we don't really need a new set of equations, but we just doctor these up a little bit. So first of all, changing all of our accelerations to minus g. There's what we have. And then what we do is we go along and change our x's into y's. Okay, and then what we have. And before you know it, putting our little subscript y's on the on our variables here, we end up with our equations, and these are what we call our free fall equations. Okay, these are our free fall equations. Okay, and you'll notice that they're the same exact equations that we were using before, right? Our free fall equations are the same equations we were using before, just our x's turned to y's and our accelerations turned to minus g. So again, notice that the acceleration here has been put in as minus g. So again, if you had a high school teacher that told you g was minus 9.8, that's unfortunate, because that's going to be a source of confusion. You've got to get that straightened out in your mind. G is a positive constant. Okay, so everywhere you see a g in this course, you just put in a 9.8. Okay, anywhere you see a small g, you just put in a 9.8. Okay, meters per second squared. That would be the units on it. And so in place of g, we put in a 9.8. So the acceleration here would be minus 9.8. We have the minus sign in the equation. Okay, so keep that in mind. The way these equations are set up, the minuses are put in there for you in these equations. Well, that one's the difference in the y position. But the minuses are put in there to indicate that the direction of the acceleration is in the negative y direction, or in the downward direction as far as a y-axis is concerned. Right? If we talked about this being the y direction, upward, things that point upward are positive, things that point downward are negative. The acceleration, of course, is downward, which is in the negative direction. Okay, so here we see our free fall equations. Again, the big three, the first three here are the most important. You can solve just about any free fall problem with those equations. So let's take a look at a simple free fall type problem where the motion is in the up and down direction. And it says, suppose you throw a ball straight up into the air. If the ball goes 15 meters above your hand before stopping and falling back down, then what was the original velocity of the ball? Well, at first reading, if you're anything like I was as a student, I read that and I would be like, well, wait a minute, is there really enough information there to determine that? Well, again, we don't add extra things into the problem that aren't mentioned, and furthermore, we don't make the problem more complicated than it sounds. I'm imagining throwing this ball upward on planet Earth. Now, did they say we were on planet Earth? No. But the assumption is on problems like this that we're obviously on planet Earth. So as we throw the ball upward into the air, we do know on planet Earth, if we ignore air resistance here, that the ball will actually accelerate at 9.8 meters per second squared downward towards the Earth. Okay? And so what I'm going to do is go ahead and draw a sketch of my understanding of this problem. And so when I do that, I sketch the ball and I say, well, let me imagine the ball being starting right here. And I'll choose that at position 0. Why not? Okay, they didn't tell me at what position it started. I choose the ball starting at position 0. That means when the ball gets up to 15 meters above my hand, that's a point where it's actually going to stop. Okay, I know something about that point. And so up here at the top, where the ball's at its height of 15 meters, let's kind of look at the problem as stopping there and thinking about the ball stopping up at that point and not really worrying about it falling all the way back down. Let's just take the beginning of our problem at the bottom here and the end of the problem up at the very top point, since we know that the ball stops up there. So what we know is y original is 0, y final is 15, v final y here is 0, and v original y, that's really what they want me to figure out. And so I've got my problem set up, got my variables that I know written down, got my little diagram showing the ball going in the upward direction, okay? And what would the acceleration be? Obviously the acceleration here is going to be minus g, but that's taken care of in my equations already. So I don't usually have to deal with this in free fall problems. It's already in my equations. Okay, so now what do? I look for an equation that will help me solve this out. I want an equation that will have v0y in it. And so as I search in my equations, again, if I write down my equations here, v final y equals v original y minus gt, v final y squared equals v original y squared minus 2g times y final minus y original. All right, I'm just jotting down these equations that we know for free fall. All right, and then the last one, y final equals y original plus v0 yt minus 1/2 gt squared. Okay, now again, those are the three big equations I told you it's important, or I think it's worthwhile to try to memorize. And as I look at those, again, it doesn't, the order of them isn't anything important, but to get those three down there, it helps me to identify what equation I'm going to use. So in this particular case, I want to get an equation that has a v0y in it. Well, in this case, if I look, son of a gun, I've got a v0y there, I've got a v0y here, and I've got a v0y here. So every particular equation in this case has a v0y in it, so that didn't help me. However, I do notice that this equation has a t in, and this equation has a t in. So in both the first and the last equations there, I would have two unknowns. I don't know anything about the time, and I don't know v0y, which is what I'm solving for. And obviously, if you have two unknowns in one equation, you're not going to be able to solve it out. So by process of elimination, probably these are not going to be the equations I'm going to start with. So we're going to take a look and get a closer look now at this equation and think about that one. Do we know v final y? Well, yeah, up at the top, we know it stops just for an instant. V original y is what we're looking for. Do we know what g is? Yeah, g is just 9.8. Y final is when it's up at the height of 15. Y original is where it started from, 0. And I know everything in that equation except my unknown, which is what I want to solve for. So therefore, we've determined the equation that we want to use. We want to use the equation that says v final squared equals v original y squared minus 2g times y final minus y original. So we pull that equation out, we jot that one down, and we start substituting in what we know. We know that v final y is 0. We know that v original y is what we're looking for, so we leave that a variable. Everywhere we see a g, we just put a 9.8. Y final, the ball up at its maximum height was 15. Y original, it started from 0. Again, polarities are important. If you didn't want to start the ball at 0, you wouldn't have to. But again, most of the time we start our object at position 0. Some books suggest to do that all the time. There are cases where not starting the ball at 0 is advantageous, and we'll talk about that some. But in this particular case, solving this out, what do we get? We get v original y is going to be the square root of a certain number, and of course that would give us a positive or negative answer for v original y. Well, obviously, because when we take a square root, remember the square root of any number, x, if I take the square root of x, the answer is positive or negative. I have two possible answers for that. Okay, so when I solve this problem out, I get two possible answers for v original y, either plus or minus 17 meters per second. But obviously, v original y, being a velocity, is the original velocity of the ball, and we threw this upward, so we're going to use the positive root, and our final answer is indeed positive 17 meters per second. Okay, signs are always important. Now, before we wrap it up for today, let's have you practice this. I'd like you to pause the video and practice trying to do this problem yourself. Down the left side of the page, I kind of have like kind of a step-by-step prescriptive solution for you there. You don't necessarily have to use the quadratic formula. If you do end up with an equation that has a t squared in it, if that's the direction you go with your problem solving, then there's the quadratic formula for you if you can't remember that. And then don't worry about the questions at the end. The questions at the end may or may not apply to you depending on how you solve the problem. But pretty much what I've got is kind of a step-by-step process here. You do this, then you do this, and you do this, and and you get your final answer. So pause the video and take a look at this problem and see if you can work it out. Okay, it says a ball is thrown straight downward out of a high window with an initial speed of 5 meters per second. Remember, speeds can never be negative, right? Because the speed is just how fast something's going. Something can't be going at a negative speed. However, it could have a negative velocity, right? Negative velocity means the object's moving with a certain speed, but it's moving in the negative direction in our coordinate system, okay, on our axis. So notice that this word is speed here. So a ball is thrown straight downward out of a high window with an initial speed of 5 meters per second, and a person 20 meters below waits for the ball to arrive. The question is, how long does a person have to prepare for the ball's arrival? So go ahead, pause the video now, try to work this out, and we'll see how you did. Okay, so let's take a look here. Here's how I did the problem. It's not necessarily the only way to do the problem. There are other ways to do it. Typically, the more complicated the problem, the more routes there are to the solution. You just want to be sure that you're taking a correct route, right? A proper route. And so in my particular case, what I did is I started by drawing a diagram. Okay, I selected that I was going to use the y-axis. Obviously, the up and down direction is the y direction. Obviously, the upward direction is positive, the downward direction is negative, and so I drew that in as my axis. It's always good to have a coordinate system. You need to have a coordinate system. And then I put the ground down here, all right, where the person's going to catch the ball. I put that at the bottom of my diagram. I released the ball from the top of the diagram. So I drew a picture of a ball being thrown downward here, okay? And I kind of put some dots to indicate the ball's coming down. I drew the ball at the bottom here, and I had it land on the ground, or that would be basically the position where the person's going to catch it down there at the bottom. So I decided, okay, here's an example where I chose y0 here to be 20. Why did I do that? Well, because I wanted to call the level where it's being caught 0. Okay, I can do that. I can choose where the object starts in my coordinate system. Okay, now if I had chosen that as 0, right, some books would say to always choose the original position of the object as 0. If I were to do that, then my y final down here is going to have to be negative 20. I've got to be careful with my signs. All right, if that's the 0 on my coordinate system up there, then my y final here would have to be negative 20 because it's 20 meters below where the object started. Okay, so if you chose y0 as 0, then y final would be minus 20. All right, if you'd have chosen, just for any random reason, what if you'd have chosen y original as 10? Right, you can start it anywhere in the coordinate system that you want. What if you just said, well, let me choose y0, let me start the height of the ball when it's thrown out the window at a height of 10. Then you would have to put the final height when the person catches it at minus 10, right? We have to have 20 meters of distance, 20 meters below where it was thrown from is where it's going to be caught. And so I have to have, my y final has to be 20 meters or 20 units less than what it was at the beginning. So if this is positive 10 up here, then it would be caught at minus 10. So really you can choose any original starting position for your problem that you want. In this particular case, I decided to choose 20 because it said it was in a high window, and I tend to think of the ground as being the 0 position. So I chose y0 as 20 and y final down there as 0. Again, what am I looking for in the problem? They want to know how long it took, so my t value there, I put a box around that, or I put a question mark there for that because I don't know how long it takes. That's what I'm looking for. What's my original velocity? Here's where I have to be careful. They told me it was thrown downward with an initial speed of 5 meters per second. But because it's thrown downward, remember velocity, remember these variables that are in these kinematic equations are vectors. They have signs associated with them, and the signs are very important. So V original here has to go in as minus 5. It was thrown downward at 5 meters per second, but it was thrown in a negative or negative y direction, right? It's thrown downward, And so the velocity arrow here, what direction is the ball initially moving? It's moving downward, and so my velocity has to go in originally as a -5. The acceleration, of course, is taken care of in my equations, but if I wanted to write it down, it would be minus g, or minus 9.8 meters per second squared. So I've got my problem set up with my little diagram drawn. Next, I have to select a kinematic equation, or in this case, a free fall equation. Going through and logically determining which one to use, I want to use an equation that has a t in it. Okay, the v final y equals v original y minus gt has a t in it. However, in this particular case, I don't know v final. They didn't tell me how fast the ball is moving when it gets down to the bottom. And so even if I know what v original y is, that would have two unknowns. So by process of elimination, you may have selected this equation. There is a way to solve, other equations and piece them together to get to the answer, which is fine. But if we choose this equation, we notice that y final, we do know that. It's 0. Y original was 20. V original y was -5. G is just a constant in 9.8. So we know everything in this equation except t. And so that's the equation I selected to move forward with, because I know everything in that equation except the t, and I should be able to solve it out with just that one equation. So what I did at that point is plugged in. Y final was 0. Y original was positive 20. V original y was -5. G is a positive 9.8. And I have an equation that ends up being a quadratic equation in t. Okay, this is what we call a quadratic equation. It has the variable term is squared. Okay, and the solution to that sort of an equation, of course, if we put it into this format, at squared plus bt plus c equals 0, then we know the equation has a solution following the quadratic formula. And so my b is my -5, my a is my -4.9, and my c here is positive 20. I plug those into this equation to solve out and get my t values. I get a t answer when I solve this. Again, remember your square roots, you have a plus or minus option, so I end up with two possible answers here. I either find out that the time that it takes for this ball to get to the bottom is minus 0.51 or positive 2.08 seconds. Again, or I'm sorry, the time is minus 0.51 plus or minus 2.08 seconds, which gives me an answer of either the time is 2.59 seconds negative, right, negative 2.59, or positive 1.57 seconds. Obviously, t equal to negative 2.59 would solve the mathematics of the equation, but realistically, time does not run backwards. If the ball was dropped or thrown downward at time 0 on our stopwatch, it's going to be 1.5 seconds after it's thrown down that it gets down to the bottom. The positive t has to be our answer here because time does not run backwards. So we have to have our time moving in a positive direction. By default, our stopwatch starts at 0, and so positive 1.57 seconds. Now again, that's assuming you use g as 9.8. If you use g as 10, you might have got a slightly different answer, but you should get an answer somewhere around 1.57 seconds. Okay, down here, this is if you had done it the way I did it. It says explain the meaning of the solution with a negative sign. Obviously, that's a mathematical solution, but it is not a physical solution. And then is the magnitude of the positive answer reasonable? 1.57 seconds. If I think about 5 meters of or 20 meters of distance, that's about, what is that, about 60 to 70 feet. And so, thinking about a person throwing a ball downward from, 5 stories high or something like that, I suppose that would be a reasonable amount of time. It certainly seems reasonable. If I got an answer of, 157 seconds, I might question that. Or if I got an answer of 0.1 seconds, I might have questioned that. But an answer of about 1.57 seconds seems reasonable. And so I can go ahead there and feel pretty good about my answer. And I can move on to the next problem. So again, this is pretty interesting because, again, if somebody did this, if somebody sets this up, okay, sets this situation up, I can calculate and predict how long it's going to take for that ball to get down there. So this is where I think the physics got to be fun. And what I started to do was I started using an almanac and I started looking up all kind of tall structures like the height of the Empire State Building, the height of Niagara Falls, and things like that. and calculating how fast things that went over those falls would be landing at the bottom of the falls. So, you know, if somebody goes over Niagara Falls in a barrel, how fast is the barrel moving when it hits the water below? If somebody were to throw a penny off the top of the Empire State Building, how fast would it be moving when it got down to the ground? And again, ignoring air resistance at this time, using our free fall equations, you can answer a lot of interesting questions like that. Now, we're starting to run out of time for today's lecture, and so just backtracking a little bit, what would be the acceleration of a rock thrown straight upward at the moment it reaches the tippity top of its trajectory? What would its acceleration be up at that very top point? Well, hopefully you remember when we talked about this earlier in class, obviously right before the ball's at the top, it is moving upward, and right after it's at the top, it's moving downward. And so the entire time this ball is in the air, if we ignore air resistance, the entire time its acceleration is going to be g towards the Earth's surface. It's going to be accelerating downward in the negative direction at a rate of 9.8 meters per second. Right? It's going, so if it was thrown up at, let's say, 9.8 meters per second, if that's was its original velocity upward, in 1 second of time, it's going to have slowed to a stop, and then with another second of falling, it's going to fall back down, and it's going to be moving at negative 9.8 meters per second after another second. Okay, so every second the ball's in motion, it's going to lose speed going up at 9.8 meters per second, and it's going to gain a speed of 9.8 meters per second coming down. And so therefore, again, if this was a second up and a second down, we'd have a velocity upward of 9.8, velocity of 0 up at the very top, and a velocity of negative 9.8 when it comes back down. So again, the entire time it's in motion, even up at that top point, the acceleration is 9.8 meters per second squared downward, or negative g. It's important to remember that reading your book and studying the problems in your book, example problems, looking at the animations and the little video clips and problem-solving clips that are available in your e-text in WebAssign, these are all important things to do as part of your study time. So read your book, read the example problems, look at the different animations and help videos and things like that that are available with your e-text. Take advantage of every resource you have and work at it as hard as you can. And each problem that you study and understand, and each problem that you try and homework and understand and work yourself through is helpful. Okay, so here's an example. This is right out of your book. This is a sample problem that is solving exactly what that previous question was just asking, where we had the ball thrown up and straight back down. And so sometimes when the ball is, for example, up at the top in this particular problem, again, there's symmetry involved, and that can be used to your advantage at times as well. So for example, if the ball is released from this height and it falls down, then the amount of time that takes will be the same as the amount of time it took for the boy to throw it up and have it get up to the top. Right? In other words, the time up equals the time down. So sometimes that can be helpful in solving problems as well. Anyway, study through this sample problem, study through as many as you can. Keep working at this. It takes a lot of hard work, and we'll have some time in our Zoom sessions to look at some problems, and hopefully I can answer questions and continue to demonstrate this process for you. Okay, and then one final thing to mention before we call it quits for today, and that is a lot of our exam questions will be multiple choice, and sometimes students wonder why they're multiple choice. And one of the reasons is multiple choice questions are just as fair as partial credit questions. Okay, first of all, I mean, if you ask a psychology person or a person who does studies and investigations into multiple choice test taking, educational specialists, they've determined that multiple choice tests are just as accurate at grading students. But there's another thing that I like about them, and that is that when you have a multiple choice answer choice, sometimes as maybe you don't know how to do the problem the entire way, but you are able to eliminate some answers, and therefore you have a chance of getting a right answer by guessing. And that does help make up for problems where you felt like, well, geez, I was really close, but maybe I forgot a square root. And you say, geez, I didn't get any points for the problem. But again, there's other ones that you're going to guess at as well, and uh, have no idea what you were doing on, and still get points for them. So multiple choice tests, I think, are in general good. Uh, and I think that multiple choice tests are a little bit more like real life, actually. When I first started teaching physics, I gave almost every question was partial credit, and it took me a lot of time to grade, and it was, a lot of bickering over points and people having hard feelings because maybe they thought they deserved more points than they got, and so on and so forth. And I thought that was more like real life. But the longer I taught, the more I realized that real life is a little bit more like multiple choice. You either get it right or you get it wrong. And this little cartoon that I remember from graduate school, I had a colleague that had it hanging on their door. It was a cartoon, something like this. I've reproduced it as best as I can with my own drawing and my own sketching there. But it was called the Bridge Design 401 Final Exam. And the student is up there on the one part of the bridge saying, don't I at least get partial credit? And you can see the bridge, of course, does not match up. It was built from each side, and when you got to the middle there, it didn't match up. And of course, that bridge is totally non-functional and not acceptable. So even if the student had been very close in their calculations or in their design, obviously that is a non-functional solution and would be considered a failure in everyday life. So take heart. Most of the time in summer classes, with the class a little smaller, I will do some partial credit, but understand that when you have large classes of 50, 60, 70, 100 students, many times the partial credit grading is just not viable for most professors, and multiple choice is used. But multiple choice questions are problems in terms of testing. Turns out to be just as fair, and it's much simpler, much faster, and for grading, and it's much more clean cut. So there's no hard feelings. You either got it right or you got it wrong. And again, the times that you feel like you got ripped off will be compensated by some times when you guess the answer right when really you didn't know. Okay? And again, I do think that multiple choice tests also help to test that ability to eliminate some answers, which is also a skill that I'd like to see how you do with as well. So anyway, expect mostly multiple choice type questions on our tests each week. There may be some partial credit, but expect mostly multiple choice questions for this reason. Anyway, keep working hard and keep plugging away and doing the best you can do. The more you work at it, generally the better it makes sense, the more it makes sense. So take care, best of luck.